Hey everybody, thanks for coming to our session. We're going to get started. My name is Chung. I'm the CEO and co-founder of LanceDB, and this is Zero.
Yeah, hi everyone, I'm Zero. I'm currently a senior software engineer at Databricks.
So I know the presentation title is a little bit different from what you see out on the sign. We decided to expand the scope a little bit to talk about not just search and analytics, but a sort of a complete Lakehouse architecture for your AI data, especially if it's multimodal. And so a little bit about me. I'm one of the original co-authors of the Pandas library. I'm working on LanceDB today for all of the AI data that doesn't fit neatly into those Pandas data frames. And I've been building data tools for about 2 decades. So this really is something that I feel super passionate about.
So a little bit about me. I work on 2 different products at Databricks, including Mosaic AI vector search and feature store products as a founding engineer. And most recently, I've led a project to completely re-architecture our vector search in the backend. And we just announced a new product offering called Storage Optimized Vector Search on this new architecture.
So what we're going to talk about today is sort of broken into 2 parts. One is we're going to do a little bit of a technical deep dive, or Zero will, to talk about the new cloud-native vector search that Databricks has been working on, and what that architecture looks like, and the problems that you run into when you build something like that, and how do we kind of solve those problems. And then we're going to talk about the LanceDB part, which is the multimodal lakehouse for AI. So how we go from a vector database to something that is more of a complete platform for AI data infrastructure. So what are the new data infrastructure challenges that AI poses, how Lance format is designed to solve those challenges, and how we can work on not just search, but all of the diverse workloads that you need to run on that AI data. And by then, it'll be clear why, even though the talk is about LanceDB, that we're talking about Databricks search here. So, and basically, what we hope that you'll get out of the talk is essentially what a modern architecture for AI data infrastructure looks like, or at least should look like, and what are the things that you need to be thinking about when you plan for such architecture.
Cool. So my talk today will mainly focus on cloud-native vector search architecture and how we built at Databricks on the vector search team a massively scalable vector database that's far lower cost compared to many of the existing solutions. And I'll start off talking about some of the challenges we see in many of the first generation vector databases. First being coupled storage and compute. This is what you get from a traditional share-nothing distributed system architecture, where you have compute nodes, and this attached to them act as the persistent storage layer. And what it means is you're effectively maintaining a stateful system. You have to manage data movements across different nodes. And for those of you who are in the seat today, operated in such system in the past, you know that it's extremely difficult to operate at scale. The second point being vector indices are mostly memory resident. To give some additional context, 4-position embeddings are huge. We can do some simple math. Let's say you have a 4-byte typical floating point. You're using OpenAI embedding model with 1,024 dimension vectors. And you have 100 million points. Just storing the full precision vector itself is, if you add that up, is over 300 gigabytes of storage. And you have to serve all of them in memory. And the actual vector index is typically larger as well because you need to store some additional info for query search scope reduction. And this is why if you see a lot of the existing vector DB products out there, they're super, super expensive. Typically resulting in thousands of dollars of infrastructure bill just to keep the index warm in memory. And the third point has to do the query pattern that's sort of inherited from a traditional search architecture. And this is what we call a scatter and gather query pattern. The idea is you have immutable data fragments, and you have indices built for each of these immutable data fragments. So these two are essentially coupled together. And the benefit of this approach is you can build and search these indices and these data fragments in parallel. It's very easy to operate, no matter what the underlying data structure is. But the downside is, first, query performance drops significantly as you scale the number of data segments. Second, merging these segments also is very costly. Specifically for vector indices, you effectively have to rebuild these vector indices when you compact data fragments and merging them. So how are we overcoming these challenges? And this is where we take the Lakehouse approach. The first is, decouple storage and compute. Your vector indices and raw data fragments live in durable cloud object storage. Query nodes are completely stateless, and it only needs to cache data in local SSD and memory when needed. We're taking a further step to decouple ingestion and serving compute as well. Ingestion runs on fully distributed in-house vector indexing engine built on top of Spark. Query runs on much lighter weight Rust services. And this is what you get with the cloud-native vector search architecture, which gives you unparalleled scalability at far lower cost by effectively leveraging cloud object storage. It also gives you high flexibility, trading off between performance and cost by simply moving data around different storage tiers. What do I mean by storage tiers exactly? So one of the most important design decisions we have to make when designing storage system is to reason about what data needs to be stored where. On the top, you can see you have memory, local NVMe SSD. These are high performance, fast storage tiers that comes at a very high cost. On the bottom, you can see something like cloud object storage, which give you slow and lower performance, but they are magnitude cheaper. And the high-level design philosophy is how can we leverage fast, high-performance storage tiers for the most computationally expensive steps and use cloud object storage, cheap storage for the rest. We've also taken a step to completely redesign the data layouts for our vector database. Many of the first-generation vector database use some algorithm known as HNSW. It stands for Hierarchical Navigable Small Word Graph. It's basically a graph index with random sharding. And HNSW index contains a graph, kinetic graph, with full position embeddings. And it's designed to work when you have the entire index serving memory. And if you blindly offload the index onto disk, it hurts query performance dramatically in seconds or even tens of seconds. So what you end up having is you have to serve this very large HNSW index fully in memory, and it's really hard to scale. And what many systems did is end up basically randomly sharding these data fragments and build separate HNSW indices on top of them to overcome this challenge. And this is where, as I mentioned earlier, you have a couple index and data fragment data structure, and you're running something called scatter and gather queries. What does it mean? It means like your query has to touch every data fragments out there for the query to complete. And this is what's shown in the graph on top. On ingestion, you have some compute nodes that's effectively building some data fragments. Each data fragment has a corresponding index in it. On query, you're doing one of the compute nodes is talking to all the other compute nodes, and you need to run the search on each of these data fragments and its vector index, and you need to do a final aggregation step to get the result back. And this is what's inherited from the traditional search architecture. And when you have many of these segments and vector indices, you end up driving up tail latencies and query compute costs, also the aggregation overhead. This is why we're shifting to AVF-style vector indices. We build a single index for the entire data set with spatial aware partitions for search scope reduction. And this is shown in the graph below. This is two-dimensional space. You're effectively breaking down the embedding space into spatial aware partitions represented by a cluster. And on query, you only need to search the clusters that are closest to your query vector. And this also requires you to decouple the index data structure from the immutable data fragments. As I mentioned earlier, updates happens independently in these two different data structures, and you no longer need to constantly rebuild these sub-indices when you add new data fragments or compact existing ones. Piecing it together, how does it actually work when we build this? We're leveraging Spark's massive scale and parallelism for ingestion. Turns out Spark is perfect for building AVF-style indices because, as you can see in the graph on top, the most computationally intensive step, which involves transforming and assigning AVF partitions for each row in the data set, can be fully parallelized on Spark. We're also harnessing state-of-the-art quantization techniques for serving cost reduction. This is coming back to the question of what data should be stored where. And quantization technique can dramatically reduce the vector index size with trade-off to retrieval quality. So we could effectively serve a heavily quantized vector index fully in memory and offload 4-position vectors in cheap storage, like cloud object storage, and retrieval quality can be compensated by doing a simple overfetch and re-rank with 4-position embedding. And in this step, you require random lookup to basically do this overfetch and re-rank. You require a storage system with really good random access performance. And this is an overview of how we re-architecture and completely redesigned our vector search system in the backend. And coming back to LanceDB is built to be a cloud-native vector store. When we initially designed this project, we had many chats with folks from LanceDB exchanging ideas, discussing architecture, and we share a very similar vision in terms of what the cloud-native vector search architecture should be. Lance file format is one of the best storage formats out there, heavily optimized for both scan and random access performance. Lance table formats supports file-based secondary indices, including vector, full text, B-tree indices, making Lance a perfect fit for building a cloud-native vector store, as I've demonstrated above. With that being said, I'll hand it to Chen to talk more about Lance.
All right, thank you. Cool. So I think what we heard from Zero is very exciting about the new product launch from Databricks, right? So to summarize, when you're building a massive scale cloud vector store and cloud search product, you need compute storage separation. You need to be able to think not just about the index, but also about how are you going to store the data, how are you going to shard that data, how are you going to associate the right data fragments with the right parts of the indices. And then you need to think about random access performance straight off of object store, right? Because if you have great indices that you can point to the rows that you need, but then it takes a million years to actually access those rows, it doesn't really help you all that much. So you need all of those things together. And this is the kind of benefits that moving from legacy formats like Parquet to something like Lance helps us build more compelling and bigger scale products and AI data products on top. Now let's expand and zoom out a little bit. Let's say you're building a new AI application or you're building an AI model, right? So search is one part of it, and it's an important part of it. You need it maybe for serving that application, you need it to do data exploration, for data curation, deduplication, but it's not the only thing that you need to think about. So when you think about end-to-end what you need, you have to maybe analyze that data. What's in my data set? Run some aggregates, compute some metrics about your data set. You need to pre-process that data, right? So maybe your pipeline started with raw PDF documents. Your model or application isn't going to run off of those raw documents. You have to go through a fairly sophisticated data pre-processing pipeline, maybe extracting text, extracting charts, tables, and then cleaning that data up, then chunking the text, and then embedding it, and then building indices off of that. And then you can serve, and then you can train models. And then finally, if you're doing fine-tuning, if you're doing pre-training or post-training, you need to be able to load your data into GPUs, multiple GPUs, sometimes in a completely different locale very quickly. You need to be able to do global shuffles effectively, and you need to be able to have great integration with your training tools. Right? So none of those things vector databases really give you the ability to do. And also, traditional vector databases also force you to copy data to a different location. And so now the rest of your AI data infrastructure has to have this like synchronization process and copy pipeline that you need to maintain and manage. If you're on the infrastructure team and your research team creates a new feature or something like that, well, now you got to go back and rethink through that pipeline. Like, okay, where does that new feature fit in? Does that feature need to get replicated as well? Does that need to get served? And so it really slows down iteration by having all your data and your workloads in different systems and scattered in different places. And so this is what I want to talk to you about today, is how LanceDB and Lance format solves that problem. So first, let's think about sort of the new world that we're in, right? I think AI represents a generational shift in data infrastructure. And what I mean by that is sort of three things. There's sort of new problems, but really old themes of one, variety. So I think, even 5 years ago, right, the 80% of enterprise data is already multimodal. So there's a lot more variety that we're dealing with, but AI has made all of this data a lot more valuable, right? So think, PDF documents, sales slides, think contracts, right? All of that enterprise data that previously was really difficult to get value out of, AI has completely changed that picture. Number two, if you think about traditional tabular data, right? Floating points and integers, those are pretty small. But now if you move to documents and images and God forbid, videos, right? These are 3 to 9 orders of magnitude larger than the tabular data that you see. So volume is much larger. And then number three is, instead of relying and being bottlenecked on sort of human finger clicking and key typing, a lot of this new data is being generated by the model, right? So we are creating this larger data much faster. So what this gives us is the three V's and AI has completely changed the three V's and created tons of new challenges for data infrastructure. So, why do we need to do this rethink, right? And why do we need new things? It's because these new problems really demand new solutions. Traditional data lakes are optimized for, as you know, tabular data, but they're not great for search. They're not great for embeddings. They're not great for multimodal data storage. Vector databases, which is the sort of the latest type of databases that have come up in the past few years, are great for one workload and one type of data, and that is vector data. But they don't generally integrate well with data lakes. They require you to copy some of your data and kind of transform it and deal with the complexities that comes with that. And they're not great for the regular tabular data, and they're not great for multimodal data. So what's the answer? Well, we think the solution. We think the solution is a LanceDB. And so to kind of illustrate the problem a little bit more, right? So if you map that analogy, right? Like instead of having Postgres, you had to manage several services. Maybe there's a B-tree service. There's a separate storage service for like the integers and and the floating point numbers. There's a storage service for vectors, and then there's a separate storage service for like your PDFs. And then you only had like REST APIs to communicate between them. All right, how far would you be able to take kind of basically the internet without this kind of like a whole concept of a database that did all of these things together for you? So this is what Lance format and LanceDB is designed to be, right? Lance format, open source, new standard for multimodal. It's right, as Zero was saying, it's file format, which basically is the equivalent to Parquet, but offers faster random access, the ability to manage both large binary and really like mixed with data. So especially with Parquet, if you're mixing your traditional tabular data with images and videos, it's very, very easy to run out of memory, and it forces you into really awkward trade-offs in how you size your row groups. And Lance format sort of gets rid of row groups altogether and doesn't force you into those weird situations. It's also a table format, and it's sort of the equivalent of Iceberg, but for AI workloads. So it's a two-dimensional layout. So a lot of times what AI use cases need to do is this very flexible data evolution where you need to add rows and then you need to add columns over time, and you need to be able to do that without copying the data. So if you have tabular data, like a billion rows of tabular data and floating point numbers, like if you had to copy some rows to do schema evolution, it's probably not great, but like it's not the end of the world. But if you have a column of images and videos, it's like, hey, your original table is like a petabyte, or you really don't want to incur that expense of that copy. And of course, the table format itself has an arrow-based API, so out of the box, it's compatible with most of your existing data lake components, and so this works really well. By introducing this compatibility layer. So Lance format basically works out of the box with all the tools that you're familiar with, and you don't need this like huge lift in how you think about your data infrastructure. And most of the time, the workloads can be the same. The code can even be the same, and it just runs faster. And then the last part is the secondary indexes. So there's a typo there. And so for index, I think in the past, I don't know if you remember, there have been attempts at creating this secondary index subsystem for Parquet. And inevitably, these things haven't gone very well and haven't really succeeded. One of the problems was that Parquet doesn't really support great random access, and so you could point to the rows that you want, and then you have to fetch the whole row group to get it. But in addition to that, the secondary indexes in Lance format also gives you, it's focused around disk-based indexing subsystem. By disk-based, I mean either local disk or cloud storage, and we have a rich types of indexes, right? So you heard about the vector indexes, but for search and higher quality retrieval, you really need hybrid index types. So you need to do full text searches, and then you need to have fast filters, and you need to be able to then do re-ranking on top of that. All right, and so what LanceDB gives you then is being built on top of Lance format. It is a single table for all of your AI data, and that becomes a single source of truth for all of your AI workloads. So you can store all of that data on object store. You can run key value fetches like you would in, let's say, like Redis or Mongo. You can run SQL for analytics on that data. You can do, let's say, hybrid searches where you can search the text and the embeddings at the same time. And of course, you can store the raw bytes of your actual data, which then you can plug into a PyTorch data loader if you're doing if you're doing fine tuning or pre-training or post-training. Cool. So the take-home messages that we have for you is one, AI has fundamentally changed the needs that we have for data infrastructure. by changing the data types and the variety of data that we need, by changing fundamentally changing the volume of data that we need to deal with, and changing the rate at which this new, larger, and more varied data is being generated. What we find is that enterprises really need a new kind of architecture for cloud native search and dealing with AI data at scale. And this isn't just another type of database, but it's something that integrates with your data lake and has a lakehouse kind of architecture on top of that, so that you can get to the scale, you can get the diversity of the workloads that you need to run, and you can do that all in one package. And this is what Lance Format is designed to do, is power this single source of truth for AI data. Cool. So one of the things that Zero mentioned was how great Spark was how great a fit Spark was for generating these sort of distributed indexes and working with AI data in memory. And so tomorrow we have another joint talk, LanceDB and Databricks, specifically focused on PySpark and the integration between Lance and PySpark. So this will be a joint talk between Lou, a database engineer from our team, and Allison, engineer on the Databricks team who works on PySpark. So if this is something interesting, highly encourage you guys to go check that out tomorrow. All right, so we'll open this up for questions. Thank you so much for listening to our talk. You can check out this QR code for the Lance Discord and check out our open source. And then I think for the new storage optimized vector search, is that the announcement or the blog?
The announcement.
The announcement, yeah. So very, very exciting launch. Anyways, so thank you. And if anybody has any questions, we'd love to take them now.